Oop. So can you see my screen? I can't hear you. Oh, wait, you're on mute, I think.
We're seeing the slides that are saved in there, so you just need to share again.
Oh, okay. Interesting. Okay, how's that? Okay.
That was great.
Okay. Okay.
Hello, everyone, and welcome to today's webinar, Optimizing Cooling Tower Water Efficiency Through Existing Routines. We'll be getting started in just a minute. And as we go through, you can send your questions to the Q&A portion of today's webinar to the chat box, which you can access by hovering your cursor over the speech bubble icon on the bottom right side of your screen. And also keep in mind that a link to the recording and the presentation slides will be sent to registrants right after the webinar. All right, hello everyone, and welcome to today's webinar, Optimizing Cooling Tower Water Efficiency Through Existing Routines. Before we get started, I do have a few housekeeping items. First, you can submit questions to our Q&A portion by sending them in the chat, which you can access by hovering your cursor over the speech bubble icon on the bottom right side of your screen. Second, a link to the recording and the presentation slides will be sent to registrants after the webinar. All right, so now I'm going to introduce Aniki Chamberlain, who will be getting us started for today.
Yes, actually, this is Tara O'Hare from EPA's WaterSense program. I'm going to introduce Aniki so that we can get started today. Aniki founded Mimir Water to equip water efficiency professionals and property owners with practical solutions to eliminate the financial and environmental cost of water waste. Aniki specializes in integrating solutions into existing operating procedures so water efficiency becomes part of daily routines. In addition to working directly with water providers and businesses, Aniki provides training courses and works to develop tools to make water efficiency easier to achieve. She recently launched a water assessment mobile app and an ultrasonic clamp-on submeter equipped with high-resolution cellular reporting technology. Aniki loves talking shop, especially when it comes to cooling towers, and it's guaranteed to have at least one submeter in her bag at all times. Aniki has a BS in Watershed Science from Colorado State University and an MS in Climate Science and Solutions from Northern Arizona University. Turn things over to you, Aniki.
Okay, did you want to talk about your next Water Wednesday at all?
Sure. Our next Water Wednesday will be on December 7th, and that'll be on evaluating water use and capital improvement projects. Now you can get started.
Okay. Great. Well, welcome to the presentation. Glad you're all here. Hopefully this is very useful for you today. Really want to focus on, as Tara said, practical solutions. So today we're going to be talking about how to optimize our cooling tower performance with our existing routines. So why do we focus on existing routines? Well, oftentimes we think for a change to be impactful, it has to be really big, but this can oftentimes be overwhelming. It seems very disruptive, and a lot of times we don't even know where to get started. So what I find is that the solution often lies within our existing routines. And luckily, all businesses have routines. Nobody shows up to work their first day and it's like, well, good luck out there. Hope you figure it out, right? We show them where to clock in or what their reports are or how we're going to move through business to stay ahead of problems, to make sure we're operating successfully. So what I find is that the most success with water efficiency is trying to tap into those existing routines. I mean, something breaks and you fix it, but it'll just break again. So how do we get ahead of those problems like we get ahead of all the other problems that we have in business of, staffing issues, budget issues, all of that? Well, water efficiency is no different. So the process of curbside recycling is a great example of what I'm talking about. So back when recycling was getting going in the 70s, right? Like, how do we get as a waste management solution, how do we get people to engage in this? Well, it turns out that people were very comfortable already putting stuff in a bin because that's where we put our trash. And once a week, they're carrying their bin to the curb. So we just gave them another bin to come to the curb. And boom, the recycling numbers went through the roof, and it was a successful waste management solution. So basically, you're getting added benefit with just very little additional work. So we call this habit stacking. How can we find our existing habits and just stack something onto it so that we can get this added benefit with little additional work? And so that's what we're going to be focusing on today, because like I said, we all have all of our businesses have routines. So how can we find where we can stack on and just make water efficiency part of our normal operating? So for starters, I always, whether I'm doing a water audit, whether I'm helping somebody to integrate this water management into their existing routines, I follow what I call the efficiency hierarchy. So first off, we're just looking for anything that could be repaired. You can change your technology, you can do whatever you want, but if your equipment isn't operating as designed, you're just going to be spinning your wheels. So basically, let's look, is there anything that needs to be repaired? Is this a mechanical issue? Is the equipment operating as designed? If not, well, we got to start right there. And this is often part of normal procedures. Most businesses, properties are going to fix what's broken. Next, we're saying, okay, what can we adjust? Is there something we can adjust for basically no cost or very low cost that's going to give us these cost and water savings that we're looking for? So then we say, okay, is this an operational issue? So similar to an irrigation controller, right? Are we overwatering? Well, do we have to replace the whole irrigation system, or can we just go and turn down the water use a little bit? So what are some adjustments we can make that are going to give us this water savings, water efficiency, cost savings that we're looking for? Next, we say, okay, everything's looking pretty good. We fixed anything that's broken. We've made some adjustments. Now, how do we tap into our existing routines so that we can get ahead of problems? It becomes our normal way of working. So is this a process issue? Is there something we're just missing in our normal way of working that could help us stay ahead of water efficiency and incorporate that? And then last, which oftentimes this is where people want to start, we have our upgrades. Like, what can I upgrade? What's the technology? So basically the repair, the adjust, and the routine is going to get you where you get that low hanging fruit, very low cost. Now, if you want to save additional water, you've got the routines, the repairs in place. What's the technology that I can add? Sometimes you go right to technology, it just depends. But in general, I follow this efficiency hierarchy to keep myself basically in this kind of most cost-effective, highest impact efficiency changes that we can make in our businesses. So this is actually similar to like, let's think about irrigation. If somebody is overwatered, a lot of times I hear people say, we're going to put in drought tolerant grass. They're using a bunch of water, but they just need some drought tolerant grass. It's like, whoa, that's way to the end, right? That's the upgrade. If somebody's got a leaky irrigation system, well, you can put in all the drought tolerant grass you want. It's still going to be using too much water, or more water than it needs. Or, if they're overwatering 4 times as much, you can put in drought tolerant grass, but they're still going to be giving too much water to the landscape. So let's go through and find these different issues. If they have perpetual leaks, what routine can we put in to address the leak? Then Once we're running as good as we can, optimal, do we then want to save more water and put in, upgrade and put in that drought tolerant grass? Or one we can all relate to is exercise, right? I literally have 3 pull-up bars in my basement because I keep thinking, man, if I just get the right pull-up bar, I'm surely going to start doing pull-ups. But turns out all these other things have to be in place because surely a 4th pull-up bar is not going to help me. So we really want to get it integrated. Then we look for those big cost, big upgrades that may be helpful. So as we go through this and we're talking about cooling towers and how to work in our existing routines, we're going to kind of make sure that we're talking about, we're understanding basically the failure points or the issues. So we can have water waste, right, where we're using unnecessary water use. We have a damaged valve and it's causing a leak. We're having overflow, something like that. And we'll talk about all that. So those things are wasteful, right? We're wasting water, we're wasting chemical, and of course, we're wasting money. Then we have damage events. Are we not using enough water? Are we scaling the equipment? Do we have something that is broken? So we don't want either of those. We don't want waste, but we don't want damage at the expense of, not using enough water. So as we go through this, we need to kind of see that we want the tower, we want to be efficient with water, but we also want to maintain the health of our tower, right? It's very important. A little bit of water waste is not near as expensive as replacing a whole tower. So as we go through that, it's important to understand these kind of the waste versus the damage and what really the priority is. Okay, so we're going to start with an intro to cooling towers, just sort of how they work. So we're just kind of cover the basics quickly so that everybody on the call is on the same page. And we're going to talk about start with simple solutions, and at the end we will get to the grandmaster of sub-metering, which is very exciting. So the way cooling towers work, we have a process of some kind. It could be a building, it could be a refrigeration system, something that is generating heat. So we want to basically get that heat out of there so that we have that nice, lovely coolness that we like for comfort or food products or whatever it may be. So we're going to take that heat, we're going to remove that heat out of the building. Typically, we're sending it to some kind of chiller. I would love to deep dive chillers today, but we got a lot to talk about, so we're not going to. But there is magic that happens inside of that chiller. And basically, we get rid of that heat and send our water back to the building, cool and ready to pick up more heat. So that's a loop that's always going. Well, what magic happens inside the chiller? We won't talk about that, but that heat basically gets transferred. And now we're going to send that heat that we don't want in our building or our process into the cooling tower. Now, cooling towers, as we all know, basically are designed to evaporate water to create cooling. So that's that they're made to use water, so we don't want to restrict that. So we send that hot water, that water that's picked up that heat, into the cooling tower. We're gonna shower that warm hot water down over what's called fill. You've probably all seen this if you're on this call. This is basically a corrugated material. Typically, there's different technologies out there, but basically what we're trying to do is increase the surface area of that water. So we've got this big fan going, we got air pumping through there, we've got hot water. So what we're doing is we're trying to get as much evaporation as we can. So by the time the water gets through that fill, it's cooled down quite a bit. Then we're going to send that cool water back into the chiller, ready to pick up heat. Can I bring it back to the cooling tower to cool it down? So this goes on and on and on, the loop with the building and the loop in the cooling tower, all to remove heat. Well, as we're evaporating water, only pure water evaporates, right? So what we're doing is we're increasing the minerals that are in the water. They're getting left behind. So we're increasing that mineral concentration. So the more we evaporate, the higher that mineral concentration gets. Eventually, it could get so high that we get basically scale forming. These minerals that are in the water, they're always trying to reach equilibrium. So if we let the mineral concentration get too high, well, it's going to harden on our machine. And inside of our chiller, effectively putting a rock, a piece of limestone basically, on a surface we want to transfer heat. So that wouldn't be very effective. So we have a sensor that's monitoring the water, mineral concentration in the water at all times. Usually it's a conductivity sensor. Well, that sensor is connected to a controller, and that controller has a set point. So that set point is saying, okay, as soon as the water mineral concentration gets so high, what we're going to do is we're going to open the drain and we're going to drain that tower. Not completely, but we're going to get rid of some of that high concentration water. So this is the industry term is basically the blowdown or the bleed, but basically it's just draining the tower. Typically it's a blowdown valve that's operating that, and that's usually an electrical solenoid valve. So that valve opens up, the tower drains. Well, if we're getting rid of water, what do we got to do? We got to fill the machine back up. So then we have some kind of what we call makeup or water supply, just a refill. Typically this is just like a float valve like you might see in the back of your toilet. Just mechanically, once the water drops, it turns on the water flow, and then once it gets back to a particular level, the water stops. And just in case that makeup valve gets stuck on, we have an overflow valve. So this is or an overflow pipe. So very similar to your bathtub, right? You're going to run a hot bath. You start making spaghetti and you forget you got a bath running. There's that little hole in the bathtub to make sure you don't flood your bathroom. That's the same as an overfill valve. So basically this process goes on and on and on, over and over, removing heat from the building, giving it to the cooling tower, monitoring the water mineral concentration in the water, draining the tower, and refilling it. Now we'll talk about cycles of concentration in a second, but the amount of times we basically reuse that water before we drain and fill the tower is called our cycles of concentration. And that's kind of our main efficiency metric that we use to understand how efficient our tower is operating. So one of the things that we will do, so who's responsible for basically understanding what the set point is and maintaining this equipment is basically this person, our service provider, oftentimes a wastewater treatment technician. Usually it's not wastewater, sorry, water treatment technician that we've hired to come in and operate this cooling tower as optimal as possible. So the balance here is to use the water as much as we can to be efficient, but not so much that that mineral concentration causes a scale inside the chiller on the tower. So oftentimes, again, what we're purchasing with this person here is a water treatment program, which typically includes some kind of chemical addition to keep those minerals in solution as long as we can to prevent them from hardening, creating that rock barrier basically on these surfaces where we want to exchange heat. So that's basically the quick overview of how towers work. So as we're looking at this, who can tell me what are some common failure points that we see? You should be able to use your chat. Let's see if I can see the chat. Well, I am not sure how to access the chat myself. So I will just go through some of them. You guys probably have already nailed a bunch of them. So common failures that we see. Well, first off, let's talk about basically mechanical failures. Where are we having mechanical, what's mechanically, where can the equipment fail? So we have, of course, any valve will always, oh yeah, here we got some good, right, faulty valves, always. You can never trust a valve. It may not betray you today, but it will betray you tomorrow. So you just have to know that every valve will eventually fail you. So yes, we could get a couple of valve failures. We have the blowdown valve. So that blowdown valve could get stuck open and it's just running water all the way through. So what kind of event would that be? Is that waste or damage? Feel free to enter into the chat box. So if that's blowdown valve, exactly, waste. Thank you, Allison. Yeah, that's waste. We're just going to have water running straight through the tower. So if that valve is open, it's constantly draining. This mechanical or this float valve is just always going to be set at that point to run, and we're running water. So this is not what we want. Probably be wasting some chemical too. May not be an emergency, but certainly not what we want. What happens if the blowdown valve gets stuck closed? What kind of risk is that? Damage, exactly. Thank you, Allison. Yeah, basically, we're going to be cycling up that high concentration water. We're not going to be getting those minerals out of there. And that's when we could potentially suffer what we call a scale event. And honestly, one scale event is pretty, can be pretty damaging, especially inside the chiller. So blowdown valve stuck open, stuck closed. What about the makeup valve? What do we see very commonly? Typically, they get stuck open, right? So if that makeup valve gets stuck open, it's going to cause overflow, right? The tower is just going to keep filling. It's going to go over that overflow and boom, right down the drain. So again, probably wasting water, or it's definitely wasting a ton of water and could possibly wasting chemical depending on how we feed the chemical. I've not typically seen it, but you can also have your makeup valve be stuck closed, right? And then you would blow down, you wouldn't refill. Again, that's going to be probably more of a damage event. Okay, so that's sort of what we're looking at with the valves. Faulty temperature sensor, any sensor can definitely become faulty. So I was at a tower in Dallas on a rooftop, 3 towers. As we're there, they're replacing one of them. And they're like, man, we're going through these things like one a year, which is pretty expensive when you think about a $150,000 to $300,000 tower. So looking through the, looking at the towers, like, man, that's crazy. What's going on? My coworker was able to see that when they had installed it, they had installed the sensors incorrectly, and it just wasn't in the flow of water. So basically, the towers were scaling up constantly and having to be replaced. So that was basically a failure in how they set it up. But yeah, those sensors, they need to be cleaned regularly. They can always fail. We can have a controller failure, right? We could have a problem with the controller that's not sending signals to the receiving or sending signals from the sensor or to the a sump heater failure. I've definitely seen recirculation pump failures, but yeah, any pump, basically any piece of equipment. Oh, popular here in Canada. Okay, yeah, yeah. A lot of places will shut them down in the winter, but that's interesting to know. And yes, pipes always can have leaks, breaks, anything like that. So the longer towers around, the more likely it is you're going to have these mechanical failures. Okay, so what do we see as far as operational failures? Something, like I said, basically along the lines of those adjustments, something that is more of a behavior-driven failure. Basically that set point, right? Ignoring HTE units. HTE, I'm not sure what you mean there. Oh, units. So we have the set point, right? So we could have set that set point incorrectly, too high, and we could get that scale, and too low, we could be wasting, right? So we want to make sure that set point is ideal for optimal performance. Oftentimes it's conductivity that we're running the towers off of because it's something that's very easy to measure, and we'll talk about that a little bit more in a second. We could have an issue with the chemical, right? Maybe I guess running out is more of a mechanical, but we could have an issue with the chemical feed, too much, too little. We could have a change in water quality coming in. I know places like, say, the Phoenix area, they switch between surface water and groundwater, and so that has a big difference in mineral concentration. So tons of stuff that can go wrong on both mechanical and operational. So we're going to do our best here to learn how to get ahead of those with some good case studies. So let's see if we covered everything. Oh. Yeah, we pretty much got it all. Valves, like you say, never trust a valve. Sensors, pumps, pipes, controller, chemical pump. We've got, the water level can often, the service provider or whoever is in charge of the mechanical side of things sets the water level too high or too low. And we're going to look at some other interesting failures towards the end, some good case studies. Okay, great job. So that's kind of your basic cooling tower. They have kind of different alignment, cross flow, counterflow. Not really that important for our purposes here, but we also might see what's called an evaporative condenser. We're not going to dive too deep into it, but I just want people to understand that if you don't see fill inside of your tower or a chiller, doesn't mean you don't have a cooling tower. Just means what you have basically is an evaporative condenser. So what we've done is basically taken that condenser where we're releasing the heat from the system and just put it, boom, right into the tower here. We're running water right over that condenser. And then we've just kind of broken up the compressor and the expansion valve or metering device. So pretty much similar, same failure points. With the chiller, you're going to get scale inside those tubes. On a evaporative condenser, you're worried about getting scale on the outside of those, the tube bundle inside of your tower. But again, we're pretty much talking the same failure points. Oh, and here we introduce, instead of the water that we're cooling going back into the system, we're basically recirculating it. So we introduce another recirculation pump. I've seen these fail, and basically there's a little sensor that once it fails, it just opens up the water flow, floods the machine, and it even sounds like it's running. The technician went and looked, he's like, no, it's running good, but they were having a 30,000 gallon a day failure. So tons of stuff that can happen. So I had briefly mentioned cycles of concentration. Again, we're not going to dive too deep into it because I want to get to some case studies, but basically it's how that's the main efficiency metric. And as we'll see through this, it's a great operating metric from day to day to see how your tower is doing. So basically we typically you measure the cycles of concentration with chemistry. We look at the chemistry of the water going out, divided by the chemistry of the water coming in, and that gives us our cycles of concentration, basically showing us how many times we've cycled those minerals up. You can do this with conductivity. You can do it with TDS, which is total dissolved solids. As long as you're comparing apples to apples, that'll give you an estimate of your cycles of concentration. Now, this is good, it's useful, but oftentimes it's just going to give us something at one point in time. What is ideal is using the water volume, the gold star for calculating cycles of concentration. Basically, what we're going to do is look at the volume of water coming in divided by the volume of water leaving, and that's also going to give us our cycles of concentration. And what's nice about that is it's giving us our cycles over a period of time. It could be a day, it could be a week, it could be a month, it could be a year. So that's, and that also accounts for basically anything that could have happened in there for sensors and things like that. So if at all possible, and that's, data is collected through submeters, which we will get to, but that is the gold star for measurement. So how do we know how much water is optimal for our tower? Well, there is an optimal value. I like to think of it as basically a cube or a volume of water that your tower needs to operate correctly and not waste. Now, this cube may be bigger or smaller depending on the year, right? Hotter years, you might have need a larger volume of water. Cooler years, less. This is same as irrigation. And we might even need 1.5 cubes just to make us feel comfortable, so we're not right on the edge of that scale. But oftentimes what we see is people are using 3 or 4 times, 3 or 4 cubes, 3 or 4 times the water they need, when really we don't need to do that. We just have an optimal amount, because scale comes typically from failure events, not from lack of water. Okay, so is there some beautiful benchmark that you can say, what's my tower cycles of concentration? Am I running efficiently? Sadly not. Each tower is basically going to have its own optimal operating based on the tower design and operating conditions, the incoming water quality, and the water treatment program that we have hired on to help us manage these things. So with the tower, here's a good example. This was a property that I was at. Look at this thing, so old, amazing. This is the chiller here. We've got the tower here. This is from like the 1950s. So this tower is getting a little bit tired, and it's definitely on the list as a capital project. So they're just kind of waiting it out. It had a little bit of a constant flow going on. So the optimal operating efficiency of this tower is going to be a little bit lower than something brand new. But when I looked at the service report, I saw that the chemical concentration was very high for this tower. So I'm like, well, that's not, if we're have a constant flow, maybe that's something that we could adjust. So we can still, even if the tower is not perfect, it's still going to have its own optimal. It's like people, it's all a unique person with unique needs. So that's the tower. It just depends on the operating conditions in the tower. Next, we kind of go into water quality. We're not going to get too deep into this because we have more interesting things to talk about. But one thing to know is that water quality is incredibly important. a very common metric for or a system for managing cooling tower water use is called a Langolier Saturation Index, the LSI. You'll probably see it on your reports. So basically, I like this as an example because it's basically showing you that it's not just one water quality parameter. A lot of times we're like, oh, we'll just test the conductivity. It's all of the way that all of these different parameters. Temperature is a big one, pH, calcium hardness, dissolved solids, alkalinity. How do all these interact with each other? What are the different levels? And that's going to help us, or that's what's going to tell us how to operate the tower. The LSI is basically a model that will tell you how if your water is more likely to corrode or to scale. Again, it's a bit theoretical, but very common. But there's also other considerations. You know, calcium carbonate is only one of the kind of impurities that could cause scale. Some places, like if you have silica in your water supply, you are in for a real treat. It's going to definitely limit your cycles of concentration, particularly once you get over about 150 parts per million, unless you have a higher pH. So, like I said, nothing we need to get too crazy about, but it is something that we need to know is important because this person right here, who you're paying money for, is kind of the key, very cost-effective key to managing correctly. So what we need to know is that this person is taking that water quality into consideration and giving us the service that we're paying for. So typically this is like, okay, you know, salespeople come in, hey, I can get you running. If you buy my chemical program and my service, I can get you running at, 4 cycles of concentration. So that's what we expect. But oftentimes when I look at reports and talk to providers, it's never really been defined what the optimal operating is. So this is your first thing, the first, and I would say most important, easy routine update that you can do to manage your cooling tower. Make your service provider accountable to the money that you're paying him. And this is done by basically asking them to be very transparent. So what I do first thing after looking for mechanical failures is work with the service provider to say, okay, first thing, can you tell us what is optimal? What is the optimal operating efficiency based on the water quality, the tower, and the treatment, your treatment method that you're selling me? Where do we want to be? What's possible? What service am I buying? So they need to give us that number. Let's say 4, for example. Then every time they come to your property to do us, to service the tower, check the chemicals, see what's going on. Usually it's about once a month. Sometimes it's every 2 weeks. Hopefully it's not any less frequent than once a month. We're going to say, you know what, you need to include your full water quality analysis that you do on the report, because that's what's going to help us make sure that we're running that cycles of concentration where we defined as optimal. Then they also need to explain why or why not we are at the observed efficiency. So let's say they say, you know what, you buy my product and my service, I'll get you running at 4. That's going to be efficient, save you water, be efficient with water, save you costs, and the tower is going to run great. Well, if they don't include this information, we don't know what they're running at. Plus, if they say, okay, you could be running at 4, and we see over time we're running at 2, like, wait a second, what's going on here? Let's reevaluate what's going on. So they need to explain to us what the observed efficiency is. Oh, we were at 2 cycles this month because we had a mechanical failure, the water quality changed, something. So just by having them, and this is industry standard. So if somebody's not doing this on your service reports, definitely ask them to. This is particularly helpful if you have a region. One conversation can increase the transparency of your entire area because you probably have the same service provider. So number 1, write that down, have the service provider be transparent in the reports. So let's take a look at a couple of those. Here's a good example. So example 1, we can see that we have some notes on the tower. That's good. Good notes about what's going on, but really, what do I see as far as chemistry? I see basically the chemistry coming in, but I don't know, or I mean the chemistry of the tower, but I don't know what the chemistry coming in is. So I'm kind of flying blind here as a property manager or a auditor or whatever my role is. So really, what we would want to do is have this person include what the makeup, what the water coming into the tower was. Like, this tower is softened. So right now I have no idea what cycles they're running at, but that's going to be important to me because that's the service I'm paying for. So here's another example. I really like this company. They're great. So what do I see different here? Well, I've got my makeup water. So, okay, I can start doing some calculations. I can start understanding, even just quick brain calculations. I can start seeing, okay, what am I looking for as far as cycles of concentration? So they've got some good ranges. What the water coming in is, the water going out. They've got some ranges of what's acceptable. So this is quite a bit of information in here. They've calculated the cycles here off of conductivity. So this is pretty good. I'm not exactly sure what our optimal is, but honestly, once I see 4.5, I'm pretty good. So let's look at what I would say is the gold star. So here we have a service report. They've obviously done all of the water chemistry. They have, the colors are amazing. I know exactly where I need to look to see if there's a problem. They've identified what the optimal range is, 2.5 to 4.5 cycles. Oh, I should have included a chart. So basically the increase between basically 1.5 cycles to 4 or 5 is dramatic. And after about 5, you start getting diminishing returns. So I'm really focused on, getting people up to around 4 or 5 if possible. So I can see what's going on. Okay, man, I'm not really looking really good on my cycles. I'm below the optimal range. So I go down here to my notes and I say, oh, okay, see the tower is constantly overflowing. So this is a really good report. This is what I would say would be what should be required of all service providers. Now, who reads the report, we're going to get into that in a second. But you can see kind of these levels of detail and service. So if you have a cooling tower and you have a service provider, I say recommend, even if it's handwritten, but they need to show you that they're doing basically due diligence every month. Okay, so we're cruising along. We got about 25 more minutes. So we're going to cruise through these case studies. So this is where the rubber meets the road, and we're going to see what it looks like at these different properties. So we have basically, let's take a scenario where we have only a service provider. These are often grocery stores, something where we don't have a technical dedicated facility staff. So common issues: overflow, stuck valves, low efficiency, just tons of unnoticed failures. We've got no dedicated facility staff. They don't have a lot of technical knowledge. I mean, you see cooling tower, it's pretty intimidating. The tower's in a low traffic area, so nobody's really walking by. We see flow into a drain and we're like, oh, that's normal. But if it's overflow, that's not good. Or if it's constant flow, that's not good either, which is tricky with cooling towers because we expect to see intermittent flow. So when we walk by a drain and it's running, that's fine. I was at a facility that literally the blowdown ran for 2 years. I was there and I was like, oh, does that run all the time like that? And he's like, yeah, isn't it supposed to? And I was like, no. And he's like, oh man, I started like 2 years ago and it was running. I just assumed that that's how it's supposed to go. The savings would be amazing. Again, the service provider, oftentimes they're doing water treatment. They show up, they fill up the chemicals and they hit the road. So if you have a mechanical problem like an overflow, they're like, not my problem. And if they're not getting good service reports, you wouldn't know. So, and then a lot of times the water use isn't communicated if you have a failure. So here's a couple of examples. Here's some cooling towers that are at a grocery store, just out back. Unless somebody's having like a smoke break, they may not see them and they may not understand what's going on with them. So definitely hidden. Again, we see a couple of examples. Here's the overflow here and the blowdown all going into the same drain, hidden behind a property. How would we ever know if something's going on? Same here. We've got multiple drains coming in. Really, it's hard for somebody to know without training and knowledge. How do I, yeah, it's going into a drain. Looks good to me. Also, with overflow, a lot of these systems are not set up to be seen very easily. This was so here's kind of, it was a video, so I tried to do some screenshots, but a tower should never overflow. We typically can identify the overflow because it's the larger pipe, almost always. I would bet $100 that it's always going to be the larger pipe. Sometimes you get to big facilities, they might be the same, but it basically has to keep up with wide open makeup valve that gets stuck on. So if you're looking in a drain, we're looking for the bigger flow. But look at this one. This one is, at least it's labeled, but man, there's no real way to tell. You have to sneak way down and look at your eye right in there, and I can see, okay, there's some flow going. So that's not very easy. What can we do to make it easier? So this pipe is labeled. Do they know who to call if there is overflow? What do we do? But anytime we see overflow, it is bad. So here's another example. We've got a couple of pipes going into this drain, but look, we've got 1, 2, 3, 4 pipes going in here. It's very difficult for somebody who doesn't have any knowledge, any training, to understand, is that good, is that bad? So things we can do. Can we label this? Can I just take a marker and write down here, overflow? I think probably, and we're going to look at some quick solutions. And this is what I'm saying. This stuff really happens. This is the tower I went to where they literally, it was behind a property. There was a service provider. The fan stopped working and the service provider just put some fans in there and took off. So you would think that that would be impossible, but no, it's totally possible. And this stuff happens all the time. So recommendations that we can do. We need to assign a tower. Who is responsible for the tower? Everybody is responsible for something at work, from custodial staff to managers. Everybody has things they're responsible for. So why don't we go ahead and include the cooling tower on one of those? They don't have to be an expert. They don't have to be an operator, but maybe we can just get their eyes on the drain every single day and let them know which drain is good, which drain is bad, or which pipe flow is okay, which one's not. Or, you know what, I get my eyes on it, the blowdown's running. Okay, it's designed to run. You don't have to stand out there. But if you come out the next day and the next day, okay, we've got a stuck blowdown valve. Always, always, always require a full service report. You're paying these folks. That's an easy adjustment. That's gonna help you get ahead of any problems. Is there an existing round sheet? What do you already do in your facility that you can just stack somebody walking by, getting some eyeballs on the cooling tower? A lot of conservation departments will come and do an assessment for you and do a lot of training to try to help auditors figure out how to incorporate this into existing procedures too. And if you're having repeated problems, you need to talk to your service provider. You need to figure out what's going on. These should not fail regularly. But a lot of times we're like, oh, it's complex. You know, I'm not sure what to do. So what can we do? We get to that root cause. And honestly, go out and get a competitive bid on somebody who might provide a little bit better service, if nothing else, to shake things up. But just see what else is going on out there. So that's properties that, again, not a lot of technical staff. You do your best to try to get your eyeballs on those drains at least once a day at minimum. Okay, now we have facility operations where the facility person is running the tower and not the service provider. So a lot of times here people are like, oh, you're a mechanic, you can run the tower. That usually doesn't work very well. Typically lack of technical knowledge, lack of resources, like do you have resources to chemicals, to sensors? A lot of times these people have multiple locations or a lot of priorities. So here's a good example. This is a pump and dump, so it just has a chiller, not a cooling tower, but is a good example. These valves here often fail. So to help this property, we basically installed a meter on the makeup, on the water supply. So if the chillers are not running, but that water is flowing, you can easily look at that and be like, boom, I got a problem. It's visible, it's a clamp-on meter, so no installation. But we also want to find routines that identify problems and inform us of long-term trends. So we set him up on a Google Docs on his phone. He goes by, he selects the day, automatically updates the number of days on the meter, puts in the meter read, and so boom, we have our gallon per day use. So not only can we identify immediate problems, but we can identify anomalies from day to day. So don't just collect the data, let's use it for operations. Here's another property. They've got a magnet system. I don't know how well those work, but their set point is at 720. So I don't know what their cycles are, but I bet it's pretty darn low. So we've got a sub-meter installed. We have a data management. We're just going to try to figure out the baseline and then go from there. This is a great example. So this is a property that has a overflow that is directly plumbed. It goes into the wall here. Took me 2 rooms later, I finally found the drain, and it's directly plumbed. You'd never see if there's overflow. So basically here's the similar tower, and they just cut that pipe and boom, now they get text messages like tower's overflowing. Super simple, on their way, and it's running on the ground so people notice. Again, here's another property that basically just drilled holes into the top of the overflow. You can see down here, perfect. Now you can tell right away if there's overflow. So it's got to be easy for your staff. Also, this property was amazing. All these towers had a ton of scale. You can see that is some serious scale. These are all evaporative condensers. They got the right person, very, very good employee, some good background knowledge, gave them the resources that they needed, chemicals, they got these sensors in, now the machines are running amazing. So they didn't expect him to just magically know what to do. They hired correctly and they gave him the resources to manage it. So again, hire appropriately, provide training. All jobs require training. Cooling towers are no different. In fact, it's very expensive if they fail. Again, train for the drain, if nothing else. What can we do in our existing procedures, and call your water conservation department. Okay, so then we have some examples where we have facilities staff and service providers. A lot of times what we see, this is hospitals, banks, we see good routines that maybe have lost their meaning over time. And the service provider, people are just like, I'm sure they're doing good, a little bit lack of accountability. So here's a good example. This was a property that, this is their building water use, does not include irrigation. So I can see these big summer spikes. So I know that that's cooling. They have a big, beautiful cooling tower. So we're looking at 100 to approximately 100,000 gallons of water use a day. So that's quite a bit. So every 2 hours, they walk around and they write down the meter reads, which I'm like, dude, that's brilliant. That's like real time. That is real time data collection, basically. So I get their 2 years of their data because they're just writing down the odometer read, putting it in a filing cabinet, and they're not actually doing the calculations. So I get 2 years of data, of course, enter it because I'm dying to know. And I see that it's saying, wait, you're using less than 1,000 gallons a day. So I'm like, that cannot be right. So go back and look, and basically a 2-inch meter had a program in it for a 5/8 inch meter. So even though we got a good procedure, a beautiful new tower, the data is meaningless because we're not using it. So we get the right program in there, and then we take all of their forms and we incorporate it into one form that they can fill out on a tablet that automatically calculates meter reads, plus makes everything graphical. So now they can see their cooling tower makeup and blowdown, automatically calculates their cycles of concentration. Plus we were able to include water softeners, boilers, tons of stuff. So we want to make routines that are optional. What actually helps us operate? And this also kept the cooling towers on the roof. Now they are looking at it every day. But if they see some change in that cycles of concentration, if it goes really low, they know that they probably need to come out here and check their overflow, things like that. So useful data covers lots of areas. Here's a good one. Here's 5 cooling towers that were on the roof. Again, they have staff, but the overflow comes out of the tower, goes into the building, and is directly plumbed. So again, we can't see it. So what would an easy fix here be? Well, how about we install a sight glass? They're walking through there all day long. So here's an example of a sight glass on a pool from a different facility, but maybe we could put an 18-inch section of clear pipe, then boom, they can get eyeballs every day as part of their normal routines. Here's another property that basically the cooling tower was out back, the overflow was out back, the blowdown drain is in the back of a mechanical room right here. So nothing very easy to get eyeballs on. And when I was there, they were having a very large overflow event. So I went back, looked at the service report. This is actually the one where it said the tower is constantly overflowing. So what this shows me is there's a gap. The service provider is telling him that there's overflow, but maybe there's no tower manager that's actually reading the reports. Plus there's a gap here in like, okay, the water treatment person isn't responsible for the mechanical adjustments. So who is responsible for those mechanical adjustments? So going back and looking at their water use, I see, dang, they've got these big spikes that happen over time. So this property would definitely benefit. So what can we do to get this into normal routines? We need to assign an owner of the property, provide a little training that when we see overflow, it's bad, or to how to read the reports. Not a ton of training, an hour would do it. There's a water meter makeup meter inside the building. Can we incorporate that into some kind of round so we can at least be writing that down every day and seeing if there's these big spikes? Then we need to define who is mechanically responsible for the tower. So these are all just slight adjustments to our existing routine that could get eyeballs on that tower and make sure these were like $16,000 and $10,000 months with water use. We're gonna running out of time a little bit, so we're gonna cruise past that one. basically setting up, I like to use Google Sheets because it allows people to enter information in the field. I can fix it from a distance, but as we're entering our makeup and our blowdown, it's automatically calculating the water use and the cycles of concentration visually. So I can see, oh man, do I have a problem or do I not right away? So again, require full service reports. See if you can update any data management into electronic where it's automatically calculating those meter reads. Everybody needs a little bit of training, even just 2 hours of training for the staff. Have them call me, I'll talk them through it. And maybe cover, cooling tower basics in a morning meeting once a month, something like that. Okay, here we get to the really interesting stuff. So remote sites or complex campuses. Basically, it's too big to do round sheets. You've got too many towers, or you're only going like once a week. Here we enter high resolution submetering, my favorite cellular submetering. So here's an example. This is water use data from a company called Apana. They're lovely. And we'll have some more information about them in a second. But here you can see this is 1 minute resolution on a cooling tower. So what I can see here we have our gallon per minute flow on the y-axis. On the x, we have our time of day. So I can see this beautiful normal blowdown pattern. The mineral concentration gets high, the tower blows down for a set amount of time, mineral concentration gets high. This is really beautiful. Everything's operating as normal. Then if I compare it to my makeup, same thing. Every time the tower drains, I've got a nice makeup that comes in behind it. Always have a little bit of flow to keep up with evaporation, but this is a beautiful, healthy cooling tower right now. So what happens if I see, oh my gosh, 1 minute resolution? I'm like, whoa, I haven't blown down for 13 hours. That's crazy. I could either be having a water waste event where I'm overflowing, and so the chemistry is not getting high enough to blow down, or I could be having a stuck blowdown valve, and that's an asset damage, right? I could be getting ready to scale up. So if I can compare it to my makeup for the same amount of time, I see, oh my gosh, my makeup is not stuck on, so I know I'm having a scale event. I go out there, this operator did a manual blowdown, fixed the blowdown valve, we're back to normal operation. Same thing, the tower filled, and we're back to normal operation. So the 1 minute resolution is amazing for submetering. This company, Apana, thanks again to them for letting me use some of their information, but basically they monitor inside, outside, and cooling systems, and they provide real-time alerts. So as soon as something goes wrong, they're going to send you an email and give you instructions on how to fix it. I also like, I use the company Metron Farnier. They also do high-resolution cellular reporting. I connected their equipment to a clamp-on meter. Here's an example. Here's my meter, and here's the what I call the Odin site. And that's going to update once a day and allow for remote sites. So a good example was this, a remote location. The person goes once a week. It's in a low traffic area. So as we were kind of talking about if this would be the right solution, we went ahead and installed some of these clamp-on meters. They're also data loggers. So I was like, let's just get some baseline data. So we install them. About 6 weeks later, one on the blowdown, one in the makeup. 6 weeks later, we come and we download the data. So the blue here is the makeup. We've got our water use in gallons over here and our time. So the water use, the blue is the water, is the makeup, the orange is the blowdown. So they're pretty in sync. But what we see is a whole week here where we had no makeup and no blowdown. It was actually on the 24th they did a service visit, and they didn't come back until the 31st. So that whole time that tower didn't run, but they thought it was because the energy management system was saying that the pump was running. So after they saw this, really he could have, if with high resolution cellular monitoring, would have come in, normal procedure, opened up the dashboard, was able to see my tower hasn't blown down or made up, I need to go to the site. So after we saw this, they were like, let's do this everywhere. So we're doing it on their cooling towers and their boilers. Very exciting. Plus, that water volume gives them the ability to manage and see what their cycles of concentration. So not only is it day-to-day operations protecting the machine, but I can see what my efficiency is. So these guys are running a little bit less than 3. After that failure, it dropped down to about 2. So they know they need to get that back up. Here's another example of Apana data. Here's a constant flow of a makeup. Boom, stuck wide open. They do the repair, and then boom, we're back to our normal makeup pattern. Also, great if you have a facility that does sewer credits. This situation, they were able to save 22 grand in 11 months just by documenting how much water they were not sending down the sewer. So you literally cannot beat the high resolution submetering. It basically is like the Matrix. I'm kind of getting low on time, so I'm going to buzz through this in about 3 minutes. Sorry about that. So here's a tower. We had really healthy blowdown and makeup, exactly what we want to see. All of a sudden, they made a change to the chiller setting, on the chiller, and we start seeing this big gap in blowdown, but also a change in the makeup. For starters, we're going to no flow, which is weird, and then a big spike. So that's strange. In the past, it had always been about 6 gallon per minute makeup, a little bit of constant flow. So this is definitely an anomaly. We keep our eyes on it, and we start seeing it happening a bunch. I mean, no blowdown for a couple of days, but these big spikes in use. So what we were able to figure out was that this is normal. You can see the overflow valve right here and the makeup valve. What was happening was the chiller was then coming on and off all the time. So when the chiller would shut off, all the water would drain out of the tower and it would cause overflow. And then when the chiller would come on, it would do this huge suck of water out of the tower and was started to cavitate the pump. And then it would, so that was that big spike of water. Then the chiller would run, it would shut off, it would drain all the water, overflow the tower, come back on, do that big drain. So we're both a waste and an asset damage event. Any sort of cellular resolution submetering you can do on rooftops is good. It's just impossible to get up there. You can't expect people to crawl up to the roof. So that here's the one that's overflowing quite a bit. And these pay back pretty quick. I mean, these events here with this meter would have paid itself off in less than a month. In about 3 days, it probably would have paid itself off. So we'll just skip over some other tips. A little bit fast on that, but I had a lot of information, so I hope you guys found that useful. Happy to talk about submeters anytime, especially the cellular resolution. So feel free to contact me anytime. We're talking about any ways to help you guys update your existing routines.
Awesome. Thank you, Anneke. That was really great, full of amazing information. We have a couple of questions here. So I'm just going to go through some of them really quick. I think you covered this, but what are the key elements for water treatment of cooling towers? An anti-corrosive, minerals, biocides, what kind of treatment goes into the cooling towers?
It's just going to depend on your water quality. If you have silica problem, it's going to be a lot different than something else, but you're always going to see an inhibitor, which is your, an inhibitor basically is just going to inhibit scale, and you're always going to see a biocide, which is going to eliminate biological growth. But it just really depends. Okay. But that's a great question for your service provider.
Doesn't the optimal cycles of concentration depend on the quality of the incoming water? Why would we expect that to be a fixed value?
Oh, it's definitely not a fixed value. Absolutely. It's going to be your tower design, your unique incoming water quality. Every place is going to be different. And then the water treatment program. So absolutely, water quality, it is the key thing to your tower. It is not going to be the same everywhere.
Are there any cooling tower training or certification programs?
You can always call me for training. I don't know about certification. I mean, from a water efficiency standpoint, I mean, obviously you could go to like HVAC school, but I do trainings on cooling towers. All hands on. We all do. We all install clamp-on meters. We'll go through all of this a lot slower and in a lot more detail. So you can always give me a call for cooling tower training. And there's, I'm sure, other ones out there.
Okay. Someone's asking about the data loggers. Do they require a cellular service or service agreement, or can they be installed in the data downloaded by site personnel?
Yeah, so I use Keyence meters, clamp-on meters. Give me a call if you want to talk more about it. I love talking about them. So these are awesome. They have a face, so you can see the flow going on. But they'll also store 10-second data resolution, a week's worth of 10-second data resolution, or a year's worth of 10-minute. That's useful, but just think, if there's a problem with the tower, you're just going to kind of see it in hindsight. Although, for efficiency, you can get a handle on that. The cellular component, again, I use Metron Fournier. They have a cellular register, awesome subscription. It's basically 10-year blocks and it's very inexpensive. So there's a lot of different options that you can do. So just give me a call. We can talk more about it.
Are there any natural treatments available for cooling towers, depending on the water quality, of course?
I mean,
I'm guessing
honestly,
that means not chemicals.
yeah, I don't know. You'd have to look into it. It's sort of like homeopathic stuff, does it work as well? I mean, usually we have chemicals because they work so good, right? It's hard to get. But so I don't really know. I don't see that very often. That one I showed you where the set point was like 728, that's a magnetic system. I honestly don't know how well they work. You'd have to look into it. I don't see them very often, but people sell them and people buy them. So there must be something to it. So that I would say would probably be your most kind of non-chemical treatment program, but you definitely would want to look into it.
What about ProMOS? I don't know what ProMOS is.
I don't either.
Okay.
Oh, yeah, it must
Whoever
be
put
a
that
water
in there.
treatment.
Yeah, it must be some water treatment thing. Do you recommend blowdown reduction solutions?
Well, it just goes back to what's your optimal tower. The tower is going to use water. We don't want to restrict it because you're going to ruin your tower. So you're just looking at how can I run this as efficient as possible? If you can get there and you're consistently running it optimal, then maybe you can go a step further and say, okay, what can we do to further reduce our use? But cooling towers, they're just made to use water and they're going to. So I would focus on what you can do to get that cycles of concentration like completely dialed in where you are running just perfect.
Okay. Someone else says, I've got an owner in a water-stressed area that wants to look at reusing water for cooling towers. Have you designed a system like this? And if so, are there any unique issues with maintenance?
It's literally no different than anything else. You're just going to have to look at the water quality and see what's coming in. So do you have enough reuse to be a constant supply? And you're just going to have to look at that. Is that water quality consistent? Can you just get a treatment program, or is it changing all the time? But really, it's no different than any other incoming water quality. Just have to see what the quality is. I assume if it's reuse, it's going to be a little bit higher in concentration in minerals before it comes in. Honestly, the probably biggest savings is just operating at optimal, or there's these things called adiabatic condensers. They're amazing. I've definitely seen them grow in popularity, but it's basically air cooled. And then once you get past a certain temperature, they bump up to where they are water cooled. They either have wetted pads that will add just a little bit of evaporation so that you can cool the condenser a little bit more, or maybe sometimes misters. So those I think are going to grow in popularity because they're way more water efficient and they'll get you through most of the time until you get to those really high temperatures.
Okay. Do you have experience with evaporation condensation? There's a new tech company called Infinite Cooling.
Evaporation condensation. I don't quite understand the question.
Okay.
I'd have to look into it. I haven't heard of that company, but dude, the technology is going bananas for water right now. I mean, these clamp-on meters, the high resolution monitoring, there's so much stuff out there right now. So I think it's, a whole new world.
Yeah, it seems like the technology has really come across in the past couple of years,
Yeah.
that it's definitely increased. I'm just going to take one more because we're running out of time, and the rest will answer via email. If you identify a blowdown problem, is this an issue that would require tower replacement, or could you retrofit the tower to achieve desired results?
I don't quite understand what you mean by a blowdown problem, but usually a tower can recover. You might have to do a little acid wash or something on it. So if you have like a blowdown problem and you have a big scale event, then yeah, you'll probably have to do some rehab. The big thing with blowdown too is you don't ever want to put a meter in anything in the line that has anything in the pipe, because you're going to have minerals and stuff. You could have a pigeon going through there, right? So you don't want anything that's going to get caught in there. So that's why I really like these clamp-on meters, because you just clamp it on the pipe and you don't have to worry about anything getting caught. But yeah, I mean, I think you don't have to replace the tower until you have to replace the tower. I think there's probably almost, I showed you that piece of scale that gentleman was using chemical treatment, and that was what was coming off the tower. So they were able to rehab those towers.
Okay, yeah, I think she just clarified a little bit to say if you identify a blowdown or overflow problem, are those issues that you would require a tower replacement or could
No,
you
no,
get
no, no. Oh my gosh, they're going to happen all the time. That's why you got to get it part of your normal routine, because no valve is not going to fail. So you just are guaranteed to have a overflow event or a blowdown valve, a blowdown event failure at some time, because it's just a valve. It's like everything else, it breaks constantly. So no, you're going to have those. That's why we got to build this into our normal routines, to get our eyes on the drains once a day, to use this cellular high resolution monitoring for remote sites, because it's going to happen. So if we can include it in our normal routine, it keeps you ahead of the problem. You can see it day one and know what to do, instead of seeing it day 30 and something's damaged. You've spent $10,000 on water, something like that. So we got to get our eyeballs on those drains every day, or get ourselves a some sort of sub-metering program that gives us the information either real time or from a dashboard.
Okay. Thank you so much. So we're going to answer the rest of the questions via email. And thank you all so much for joining us. Thank you, Anneke. You did an amazing job. We really appreciate all this information about cooling towers. And I hope the rest of you have a great rest of your day.
Thanks so much.